Hello everyone, welcome back to my YouTube channel. This is episode 2 on our building vector database from scratch. In this, we will start really building our vector database. In this, we will try to not use any existing databases or the existing libraries. We will just do the Python list or the NumPy and basic mathematics. So let's get started. So what we will cover in this episode, we will see what are most three crucial operations for any database, how they internally work as a data structure, how the brute force search works. We will use Euclidean distance metrics in this case, and how the complexity will work for the time complexity will work for the Euclidean distance, or the for the brute force it would be O of n. I will show you how it works. Uh, what we built versus what's missing in our data base, and at the end we will see like this is at the core of every vector database. Rest is optimization on existing databases. So let's look into our very first slide. What are the three core operations at the heart of any vector database or any other database? So it would be add operation. In add operation, we will keep inserting new data to our existing database. So that is store a vector with its metadata. So that operation is add operation. That's the add operation. Next is search. Whenever there is a new query vector, you have to search on your stored vectors. And the last is delete. If some document is not useful or some vector is not useful, we need to remove that vector. And everything else like persistence, like once you created vectors, once you added those, and let's say if you want to come tomorrow and query again, then we need persistence. So that is a separate thing. uh, if you keep adding vector data directly to your database without any indexing or in any order, then that will create problem at the search time. So we need indexing. Or let's say if you add some vector data with some metadata, let's say you are adding book title as a vectors, and then you are keeping author name as metadata, and you want to filter on particular author. So those all operations are like for optimization on top of these three operations. But these three operations are considered to be the core principles of the any database or vector database operations. So let's look at our vector database, how one document will look like. So in our each uh, document in our vector store will have an ID. Let's say we are giving it integer, let's say it would be 42. Then we will have a vector which represents the actual numbers, and let's say we are choosing dimensions of 128. So we will have the array of floats, and which will have the 128 floats. And then let's say if we have some metadata as well, so that goes as, let's say we have author and the author name. So we can use this Python dictionary as one record, and we can use we will use NumPy in actual code, but eventually you can store these dictionaries as a list, and that will become your store operation. So now let's say next comes once we add those vectors into one list, then we need to search also. So let's start with the brute force. In brute force, what we'll do, we will take the query vector. Let's say in our index we stored vector 0 to vector 999, that is like total 1000 vectors. So we will take the query vector and each individual vector, and we will calculate distance between these two vectors. So it would be query vector versus vector 0, and that distance is 0.12. Then query vector and vector 1, and that distance is, let's say, 0.87. Similarly, we will calculate all 1000, and then we will sort that, and then let's say user wants top k as 3. So we will say which three vectors are having similar or very close distance between these out of these 1000. So let's say vector 0 has 0.12, vector 2 and vector 7. These are the very close to vector. And then we can say, okay, these documents are very close to the query. And then we will use these information for other application, reg or similarity or classification, whatever our application is. So check every vector and then sort on the distance, and return the closest. That's all the search part. That's it. So how we calculate distance? In this episode, we will be using Euclidean distance and how Euclidean distance is calculated. So D is denoting distance, A is a vector and B is also a vector. That would be square root of sum of A minus B whole square. And if we look into the code part, it would be like define Euclidean distance, and it will take A as a vector and B as a vector. Then we will define distance initially to be 0. Then for the length of dimension of vectors, we will iterate over that many times, or we can take any A or B, any of them, and take length of that. That would be our vector dimension. And we will keep appending subtraction between vector A's and B's element wise difference and its square to the distance. And once we do for all outside the for loop, we will take a square root of it. That's all on the distance calculation. So next is how our search is performing. So let's say if we have 1000 vectors, we have to do 1000 calculation of distance with the query vectors. If we have 10,000 vectors, we have to do 10,000. Or let's say if we have 1 million vectors, then we have to take our query vector and calculate distance against all those 1 million vectors in our database, and then sort it and then get the top 3 or top 5 or top k elements. So let's say if you double the vectors in your database, then you have double the search time, and it would be every time whenever you increase the number of records. So it's linear O of n, and this is very bad, but we are designing a series which is databases from scratch, and how we can improve this, that we will discuss in the next episodes. So what we have built in this and what's missing. So we have created how we can add vectors to a vector data store, how we can search on them with the brute force and nearest neighbors. So it's like distance and sorting. And deleting is like we already have our records with ID, vector and metadata. So if user gives a ID, and we can remove that ID document from our list of documents. And distance we used is Euclidean distance. But what's missing in our this database design is better distance metrics. Euclidean is not not the best measurement of the metrics in the terms of distance. Next is metadata filtering that we will do in our next. Currently we were doing, let's say we have 1000 vector, we were doing calculation for all 1000. But let's say if you want, let's say we have book titles as vector, and if you are interested in books from only one author or something, then you need the metadata filtering. This is sublinear search, we will discuss later, like currently linear search, but you can optimize on that. And then we will discuss in episode 12, we want persistent data. Let's say once you created vector embeddings for, let's say, millions of documents today, and you do not want to lose them, right? Because you will use your application, queries can keep coming, but you will have your once vector database created that should be persistent. Code walkthrough, we are building naive vector store. So we will implement this with brute force vector store. In this we are importing only two libraries, which are time and numpy. Time we will monitor, like if we are having 1000 vectors in our index, and then how our brute force performs. Or let's say if we have 100,000 or million or more than that, then how it performs. So let's define a class that is naive vector store. So this is minimal vector store using brute force linear scan. So we will instantiate our class with the dimension. So it says like what should be length of our each vector. We will set 128 in our database. Then we will have vectors as a list of numpy arrays, and metadata would be a list of dictionaries, and those are like would be having same length, and each vector will have corresponding its dictionary. So we discussed in our theory there are three base operations. So very first is the add operation. In this we need to pass a vector and its metadata, and first we will assert it should have the same dimension where we initiated our class, and each vector length should be 128. And once that is asserted, Then we can just append vector to vectors and metadata to the metadata array. At the time search, we will need a query vector and we will need the k. How many number of similar or the nearest vectors we need. So we need to assert our query should have the same vector length as our data set or our data which is already indexed. Once that is asserted, we will have our query vector and we will use the numpy for faster operations. We will say query. At the end, distance will be sorted and we will return the top k, top 3 or top 5, whatever is required. In our case, it would be 5. This is just to show the vector length. Now this is the main function where we will have some orchestration code and a real application. So I will skip the orchestration code and I will just walk you through what we need to pay attention. So we are setting dimension to 128, n vectors to 1000 and k equal to 3, and we will create our instance of the naive vector store class and with the dimension of 128. Once that is done, then we will create all vectors. And how we will create all vectors? We will use np.random.rand module, and then we will pass, we want to create 1000 vectors with 128 dimension, and then we will start a timer and we will end the timer once all those 1000 vectors along with their metadata is inserted into one list, and that is our store, the class we defined. So in this metadata we are creating two keys. One is id, which will be the index, and one would be the label, which is item number or the vector number. Then we need to select some query vectors. So we can generate separate query vectors also, but I will choose 3 from the existing 1000 vectors only. So we are selecting 0th index, 500th index, and 990th index, 99th index as the our query, and we will run this query 3 times. So we are iterating over the query indices, and for this we will use our search method on the store, and we will pass our query, and along with we will pass k, which is default 5, but currently we have set to 3. We will return the 3 nearest vectors only, and at the end we will have the some summary about this. So let's run and see. So run completed. Let me show you. So if we see, it generated 1000 vectors with 128 dimensions, and if you see the time, it was very quick because there are 1000 vectors only and with very less dimension, which is 128. But in real life applications, this dimension would be very high and you will not have 1000, you will have the million or billion of vectors. So in the first query, we used item 0th as our query vector, and if we check item 0's query with the actual item 0, that distance is 0 because both vectors are the same. But if we look for the nearest neighbor, that is 544th and 307th vector. These are the nearest neighbors. Similarly, if we take 500th element as query, and then if we compare these, then we get this. And if we take this vector as our query vector, then its own distance would be 0, but these are the two similar because our k is 3. Now if you look at the distances, these are like around 1.8, 1.9 or 1.9 milliseconds. Now let's say again we go to our code base, and instead of 1000 vector, let me change it to the some larger number for just example. So instead of 1000, let's have the 10,000 vectors 10 times, and run again same script to see the difference. So if you see now, it created 10,000 vectors of the same 128 dimensions, but if you see this time insertion, that is increased slightly. Similarly, if you again take item 0th, its own distance would be 0, but this time if you see the nearest distance, that is coming from 9162, that is nearest neighbor and then 1589th vector. But if you see the time from 2 milliseconds for 10,000, it becomes 26 millisecond, 25 milliseconds, 22 milliseconds. So time itself become 10 times. So that's the drawback with the linear search. And if you look at the summary, what would be the size of our store? That would be like 10,000 vectors, 128 dimension, and whatever precision we are storing, float 32, float 64, or like whatever precision we will use. Uh, Insertion time is like how much time it is taking to insert into our new vector database. Then search approach is linear. It compares against all the 1,000 or 10,000 vectors or whatever uh, vectors we have in our index, and it will give the shortest distance and the shortest neighbors, whatever we need. So time complexity, it becomes O of n, which is bad, that we will improve in our next episodes. This works fine for like say 1,000 vectors, but imagine if there are like 1 million, 10 million, or 100 of millions vectors, then it will not scale. So for that we need smarter indexing, and that we will discuss in our upcoming episode. So at its core, every vector database is doing exactly what we have just built. Uh, Find nearest vector to a given query. Everything else is optimization. Uh, this is episode 2, and see you in episode 3 on the vector database from scratch full series. Thank you for joining.